Welcome, data professionals and architects. Today, we are embarking on a comprehensive journey into Snowflake Cortex Search. I will be your senior trainer, guiding you through the mechanics, architecture, and real-world application of this powerful feature. Let's start by defining exactly what Cortex Search is. In the modern data ecosystem, users demand instant, intelligent access to text data. Cortex Search is a fully managed service natively built into Snowflake that delivers low-latency, high-quality search over your unstructured and semi-structured text data. We refer to it as hybrid search because it doesn't just look for exact word matches, it understands the semantic meaning of your data by combining vector search with traditional keyword search. Why is this a game changer? Historically, building a search engine required you to extract data, manage complex embedding pipelines, and maintain standalone infrastructure. Cortex Search eliminates all of that. By automating the heavy lifting, you can focus purely on building next-generation retrieval augmented generation, or RAG, applications and highly responsive enterprise search bars directly on top of your single source of truth. Looking at this architectural flowchart, you can clearly see the elegance of the Cortex Search pipeline. On the far left, we have your raw Snowflake data tables. Instead of building complex ETL pipelines to move this data out, Cortex Search continuously syncs directly from these tables. The data flows into the managed Cortex Search service, which automatically bifurcates the processing into two distinct engines: vector search for understanding contextual meaning and keyword search for exact lexical matches. These two streams converge into the hybrid engine, which intelligently combines the signals. Finally, this highly refined, searchable index is exposed through a low-latency API endpoint. This means your downstream applications simply make an API call and receive sub-second, highly relevant search results, entirely securely within the Snowflake perimeter. Now that we know what it is, why should you adopt Cortex Search over a traditional external search engine? The most profound benefit is the absolute elimination of infrastructure maintenance. You no longer have to worry about provisioning vector databases, manually tuning search quality parameters, or orchestrating complex, fragile data pipelines to refresh your search indexes. Everything happens natively. Furthermore, security is paramount. Cortex Search services perform searches using owner's rights, meaning they follow the exact same rigorous security model as other Snowflake objects. When you create the service, you define a target lag, and Snowflake automatically ensures your search index stays fresh as the underlying data changes. Ultimately, this service is explicitly designed to be the retrieval backbone for your large language model applications, integrating flawlessly with Cortex AI functions to provide grounded, hallucination-free AI responses. This comparison diagram perfectly illustrates the paradigm shift Snowflake offers. In the top, traditional approach, track, your raw data must be extracted, transformed, and loaded into an external vector database. This introduces massive operational overhead, latency, and crucially, security risks because your data leaves its governed home. Now, contrast that with the bottom, Cortex Search approach. The raw data remains exactly where it is. The managed Cortex service acts directly upon it, maintaining native role-based access control security automatically. Because the compute, storage, and orchestration are fully managed by Snowflake, your team achieves instant return on investment. You bypass months of infrastructure engineering and jump straight into delivering business value through high-quality search and AI applications. To truly master Cortex Search, we must understand its core, the hybrid retrieval engine. Under the hood, Snowflake employs an ensemble of retrieval and ranking models to guarantee top-tier search quality without requiring you to be an AI tuning expert. When a query comes in, it executes two searches simultaneously. First, the vector search uses advanced embeddings to find semantically similar documents that mean the same thing, even if they use different words. Simultaneously, the keyword search looks for exact lexical matches, ensuring specific product names or IDs aren't missed. But Snowflake doesn't stop there. The results from both searches are combined and passed through a semantic re-ranker. This final re-ranking step intelligently evaluates the combined results and reorders them to ensure the absolute most relevant documents appear at the top. You also have the flexibility to choose the underlying embedding model, such as the highly efficient Snowflake Arctic embed models, tailoring the engine to your specific language and performance needs. Let's trace the lifecycle of a query through this flowchart. At the top, the user search query is ingested. It immediately forks into two parallel processing streams, the vector engine for semantic matching and the keyword engine for lexical matching. This dual approach ensures we capture both intent and exact terminology. The outputs of these two engines flow into a union node, which combines the candidate documents. This combined pool is then fed into the semantic re-ranker, the diamond node in our diagram. The re-ranker acts as a highly intelligent judge, evaluating the nuanced relationship between the original query and the merged results, ultimately outputting the final top K, highly relevant results. This sophisticated pipeline happens in milliseconds, completely abstracted away from the developer. Now let's talk implementation. Creating a Cortex Search service is remarkably straightforward, executed via standard SQL. You use the Create Cortex Search Service command, specifying the exact text column you want to make searchable using the on keyword. A critical parameter here is target lag. This tells Snowflake your freshness requirement, for instance, 1 hour or 1 day. Snowflake will then automatically manage the background compute to ensure your search index never falls behind this defined lag. Furthermore, search isn't just about text, it's about context. By defining attributes, you can index additional metadata columns, like region, agent ID, or category. This allows your application to apply strict filters during the search phase. Finally, you assign a virtual warehouse to the service. This warehouse is solely responsible for the heavy lifting of refreshing the index and computing embeddings when the underlying data changes. This architecture diagram demystifies the creation and maintenance process. On the left is your source table or view. The flow from the source to the virtual warehouse is governed by the target lag refresh cycle. When the lag threshold is reached, the virtual warehouse spins up to process any new or changed rows. It generates the necessary vector embeddings and updates the central Cortex search index. Inside this index, you can see two distinct zones, the searchable text derived from your on column and the filterable attributes derived from your metadata columns. Because the heavy compute is isolated to the virtual warehouse during refresh cycles, the actual querying of the index later remains lightning fast and highly concurrent. As your applications grow in complexity, a single search column may not suffice. Enter multi-index Cortex Search. This advanced feature allows you to index multiple columns simultaneously, granting you immense flexibility. Imagine an e-commerce catalog. You want semantic search on the lengthy product descriptions, but you need exact, rigid lexical matching for product SKUs or brand names. Multi-index allows you to designate descriptions as vector indexes and SKUs as text indexes within the same unified service. Furthermore, if your data science team has already spent time and resources computing highly specialized, custom vector embeddings using external models, you can bring your own vectors, BYOV. By simply passing an array of numbers cast to the vector data type, Cortex Search will ingest them directly, saving you the cost of re-embedding while still leveraging Snowflake's ultra-fast retrieval engine. This class diagram breaks down the structure of a multi-index Cortex Search service. The main class, Cortex Search Service, exposes the overarching search and filter methods. However, it is composed of two distinct subclasses, the text index and the vector index. The text index handles attributes like product SKU and brand name, specializing in exact lexical matching to ensure strict accuracy. Meanwhile, the vector index handles verbose fields like product description and user reviews, utilizing deep learning to match on semantic meaning. When an application queries the main service, it transparently orchestrates across both index types, returning a highly optimized, composite result set that perfectly balances precision and contextual understanding. While Cortex Search provides excellent default ranking, true enterprise mastery requires fine-tuning. We achieve this through scoring customization. You can drastically alter the final search results by applying numeric boosts. For example, if you are searching internal wikis, you can boost articles that have higher view counts or likes. Conversely, you can apply time decays. If you are querying news feeds or financial reports, you can configure the system to gradually decay the relevance score of older documents based on their creation timestamp, ensuring the freshest data floats to the top. You can even override the default component weights, deciding exactly how much influence the vector score has versus the keyword score. Finally, if you are building an application where millisecond latency is absolutely critical, perhaps in high-frequency trading alerts, you can entirely disable the semantic re-ranking step, trading a slight drop in accuracy for maximum speed. Let's walk through the scoring customization pipeline visually. The process begins on the left with the raw search score generated by the base hybrid engine. The system then encounters the first decision node, apply boosts. If configured, metadata like views or likes acts as a multiplier, resulting in an increased score. The flow then proceeds to the second decision node, apply time decay. If the document has an older timestamp, a mathematical decay function reduces its relevance, yielding a decreased score. Finally, these modifiers aggregate to produce the final ranked output. This pipeline guarantees that the highest-ranking documents are not only semantically relevant to the user's query, but also contextually authoritative and temporally fresh. Let's crystallize this with a powerful, real-world use case. Imagine a global enterprise customer support center. Agents currently waste countless hours digging through thousands of historical, resolved tickets to troubleshoot new, complex issues. We can solve this instantly by building a Retrieval Augmented Generation, or RAG, chatbot. When an agent types a question about a new router failure, Cortex Search acts as the retrieval engine. It scans the entire database of past tickets, using hybrid search to find the 3 most contextually and lexically relevant historical solutions. Next, we take these top 3 tickets and inject them as context into a prompt for a Snowflake Cortex LLM, using the AI complete function. The LLM reads the historical context and generates a precise, grounded, hallucination-free instruction guide for the agent. What used to take 45 minutes of manual searching now takes 2 seconds. This sequence diagram details the exact flow of data in our RAG chatbot use case. The human agent initiates the flow by asking a natural language question in the chat app. The chat app securely calls the Cortex Search API, requesting the top 3 relevant documents. Cortex Search instantly returns the historical tickets. The critical step happens next. The chat app bundles the agent's original question together with the text of those top 3 tickets and sends this combined payload to the Cortex LLM. The LLM processes this grounded context, synthesizes a clear resolution, and sends the final, actionable answer back to the agent's screen. The data never left Snowflake, and the agent receives a perfect, customized answer. Finally, as senior architects, we must understand cost governance. Cortex Search costs are divided into 3 main pillars. First is warehouse compute. This is the virtual warehouse you assign to handle the heavy lifting of indexing and refreshing data based on your target lag. Second is serverless serving compute. This powers the low-latency API endpoint and is billed based on the gigabytes of data indexed per month. Third is the embedding token cost, which is a fractional charge incurred whenever new text is converted into vectors during an insert or update. To optimize, keep your refresh warehouse size moderate, usually a medium is plenty, and bundle your data updates to minimize frequent micro-refreshes. Thank you for joining me in this deep dive. I invite you all to like this video, subscribe to our channel, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. This final breakdown illustrates the financial mechanics of Cortex Search. At the top, we have the total Cortex Search cost, which branches into our 3 pillars. On the left, warehouse compute is directly optimized by tuning your target lag parameter. Less frequent refreshes equal lower warehouse costs. In the center, serving compute is highly predictable, billed entirely on the volume of data you choose to index, measured in GB per month. On the right, the embedding token cost is highly efficient because it is incremental. You only pay to generate embeddings on brand new or updated rows, not the entire dataset. Understanding these 3 levers gives you total control over the performance and economics of your AI search applications.